Hey, good morning, everybody. So what we have in front of us here are our intro to moles notes. So what I would like you to do is, with this video, I would like you to follow along in your notebooks. And I'm going to guide you through it. You're going to hear my voice going through these concepts. So feel free to pause or rewind at any time to catch up on what you are writing down or review something that you may have missed, right? As always, reach out to me via Schoology message, and when you're done, you can go ahead and start your active practice for this. So, let's review. We want to talk about how substances can be measured in different ways as a review, and you learned about this in your Intro to Moles guided practice that you completed last week. So, if we want to count something, there are a couple of ways that we can count something. We can count the number of something, right? We can say that there are 5 apples or a dozen eggs. We can count the mass of something. So even if we are still working with the example of eggs, we can count how many eggs we have. We can count how much that egg weighs. And we can also crack open that egg and see how much volume the liquid inside contains. So we can measure substances by count, mass, and volume. This also applies in chemistry. We can measure any chemical by count, by mass, or by volume. So let's use the example of gold bars. If you walk into like a really fancy bank vault, you can count, okay, there are 100 gold bars in here. But you can also take one of those gold bars and weigh it. Oh, it's however many grams or however many kilograms. And then we can also, if we needed to fill a duffel bag, like a 50-liter duffel bag, we can put all those gold bars in it and take them away. We're not going to do any of that because we're not bank robbers. But those are all the ways that we can measure substances. So gold is obviously a chemical, but other ways that we can think about it are how many atoms that we have, or what is the weight of all the atoms that we have? And then does that substance fit into a container? That's how we're measuring volume. So the mole, as a unit in chemistry, serves as a bridge between the atomic and the macroscopic world. So atomic meaning particles that we can't see, but we do know exist, and what we can see. So if we were to look at one of those gold bars, how many atoms are in one gold bar? The way that we would quantify that, and it can be quantified, is through the word mole and a special number called Avogadro's number. So either right now, you can pause this video and then go to our Google Classroom assignment and watch this video of Mr. Anderson explain Avogadro's number and the mole, or you can wait and watch it after that we're done. But this video is going to be super useful to help us think about and ingrain this concept of the mole. So I'll let you decide now, are you going to pause this video, watch it quickly, or are you going to wait and watch it after we are finished? I'll pick back up in 3, 2, 1. So a mole is 6.02 times 10 to the 23rd atoms, molecules, or formula units. So this number, our 6.02 times 10 to the 23rd, that's our Avogadro's number. We know that Avogadro said this is how many atoms or molecules or formula units make up 1 mole of something. And so if we were to write that all out, it would be 602 sextillions of atoms, molecules, or formula units. So thinking back to our gold bar, if we were to put that under a microscope, a really powerful atomic microscope, and look all the way to the tiniest little substances, this is how many atoms we would need to count. Oh, so many. So thank God Avogadro did that work for us so that we have this number, and all we need to do is the math to convert between particles and moles, or moles to particles. Thinking back to dimensional analysis, we know we've been talking about conversion factors this whole time. This is our, no pun intended, solid gold conversion factor. So let's go through a couple of examples. How many atoms are in a 1.22 mole sample of sodium? We know that the particle that we are looking for when we talk about elemental sodium is an atom, right? An atom is a base unit of that element. With dimensional analysis, we're going to set it up such that we're going to take what we know, use a conversion factor, and turn it into what we don't know or what we need to find. So what we know here is we've got 1.22 moles of sodium. We want to convert that into atoms, and we're going to use our conversion factor of Avogadro's number. I'll show you how we do it. First, we take our known, we put it in the numerator, we put that over the number 1, right? We have one of these things. We are then going to multiply by our conversion factor such that the units cancel. We do not want to have moles as our final answer. We want to have atoms. So we're going to take Avogadro's number, right? However many particles we need to make a mole, 6.02 times 10 to the 23rd atoms of sodium make 1 mole of sodium. We know we have about a mole and a quarter. We're then going to multiply these two numbers together, cross out our alike units, and we end up with our final answer. Now, let's double check our work. Does this make sense? Getting rid of our exponents here, I'm like covering up what I see on screen. I know you can't see me do that. But basically what I'm trying to ask is 1.2 times 6 about 7.3? Yes, and then we're going to keep continuing our large group of exponents here. So our final answer is 7.34 times 10 to the 23rd atoms of sodium in this many moles. So conversely, we're going to ask how many moles are equal to this many molecules. In this example, we are working with carbon monoxide, carbon single oxygen, carbon monoxide. So we know that there are this many molecules. Now hold on. Let's look at the exponent here, and predict. We know that a mole is 6.02 times 10 to the 23rd. So already can we predict, is our final answer going to be more than 1 mole or less than 1 mole? So we've got our known is how many molecules we have. We want to go to moles. Our unknown is how many moles of carbon monoxide. Once again, we're going to use Avogadro's number to convert between the two, but we want to make sure that our units are still canceling. So as always, we put our known over the number 1, 4.79 times 10 to the 24th molecules of carbon monoxide. We're actually going to divide this time because we want our units to cancel. We want molecules of carbon monoxide to cancel each other out such that we are left with moles, our desired unit. So we're going to divide these, but remember, 10 to the 24th is one power bigger than 10 to the 23rd. So we're going to be left with 7.96 moles of carbon monoxide when we divide, given that this is actually 10 times bigger than this number. Ooh, factor of 10. So continuing on, let's think about how we can go between atomic mass and molar mass. So the atomic mass on the periodic table is the mass of a single atom in the unit atomic mass units. The good news is that when we use Avogadro's number, converting between the two is actually pretty simple, okay? So atomic mass units, we know that that is the weight of the protons and the neutrons that exist in an atom's nucleus. In this case, we've got, given the isotopes and everything too, carbon is equal to 12 atomic mass units. If we want to measure the molar mass of carbon, what we want to do is take the mass of 1 mole of a substance. Guess what? It's equal to the atomic mass, but our unit, instead of AMUs, it's going to be grams. Avogadro's number allows for us to make this conversion quite simple. So 1 mole of carbon atoms is equal to 12.01 grams. 1 mole is in grams, right? 1 atom is in AMUs. So if we take all of the atoms and add them together for elemental carbon in order to get 1 mole, it's going to be the same number as the atomic mass units, just in our scale of grams. Meaning grams is about 23 powers greater than AMUs, right? Raised to the power of 23. What we can do with molar mass is then take a substance, right? This substance here, dialuminum trisulfide. How much does it weigh? What is the molar mass of this substance? We can take that weight by multiplying the number of atoms times that atomic mass. So we've got 2 aluminum atoms. We can multiply those 2 by the atomic mass of aluminum. That's going to be 26.98 AMUs. We've got 3 atoms of sulfur. We know that that mass is 32.07 atomic mass units. So we've got 2 times 26 equals 53, 3 times 32 equals 96.21. We want to make sure that we're staying with our significant figures here. So we're only using 2 decimal places in this example. And we just add those together. 150.17 grams of dialuminum trisulfide is equal to 1 mole. So 1 mole of this substance is equal to this much weight. Like if we were in the chemistry lab and I had this dialuminum trisulfide in a jar, I'm pretty sure it's a solid at room temperature, I could say, hey, go get me 1 mole. You would be able to go to the scale and measure out until we got 150.17 grams. That's going to tell us what 1 mole is. Additionally, let's do it again with tribarium diphosphate. 3 barium atoms, 137.33 times 3. 2 phosphorus and 8 oxygen, right? So we're going to use our subscript here. Remember, it's like factoring. We actually have 2 phosphorus and then 2 times 4, 8 oxygen. So we're just going to add up all the masses here, 400 plus 61 plus 128, meaning that if we want 1 mole of this substance, we're going to need a lot of grams. 601.93 grams of tribarium diphosphate is equal to 1 mole. Additionally, we can go the other way. So what is the mass? Let's say we know how many moles we have. How much does that weigh? What we want to do is take what we know, 1.33 moles of tribarium diphosphate. We want to multiply that by the molar mass, what we just calculated. So if you have a word problem like this, what is the mass of 1.33 moles of a substance? You're going to need to calculate how much 1 mole weighs. We did that in the last example. We've got 601.93 grams is equal to 1 mole. Bada bing, bada boom. We're going to cancel our units and get our final answer. So the mass of 1.33 moles of tribarium diphosphate is equal to 801 grams. Let's do a longer one. It's going to be the same as the last problem, except for we have not calculated the molar mass of this substance, calcium chloride. So we've got 157.8 grams of calcium chloride. We want to go to moles. What we need to do is calculate the molar mass of calcium chloride. Here we go here. We've got 1 calcium, so 40.08 AMUs. We've got 2 chlorine atoms, 2 times 35.4. We know we've got 110.98 grams, because we know that this is the molar mass, right? doing a quick conversion in our head, assuming that because we're in moles, we've already used Avogadro's number to go from AMUs to grams. So we've got our known. We have 157.8 grams of this. We want to know how many moles that is. We are going to set this up such that our units cancel. We take our known, we put it over our conversion factor, right? The molar mass of calcium chloride is the conversion factor. So 1 mole of calcium chloride is equal to 110.98 grams. Cancel out those units. We're left with our final answer of 1.422 moles. Let's think back. If this is the weight of 1 mole and we have what we have, does that make sense? Is it about, is it twice? Do we have 220 grams? No, right? Is it less than 110? Do we have less than 1 mole? So we can start to use some of our critical thinking skills to predict what our final answer is going to be to make sure that we are setting this up correctly. All right, so those are all the examples that I have for you. You're going to have an active practice that you can look at. As always, let me know if you're confused. I would highly encourage you guys to do this work in your notebook before you put it into our assignments online, just so that you know that you can do this work authentically. All right, well, that's all that I have for you. So have a great day. Let me know if you have any questions. See you guys later.